So this talk, I'll present basically the process we've been doing. Just a second. So my name is Itamar. I work for Bazila, an Israeli company. We'll see what we do in just a second. I started there about a year ago, and I'll show you how the system was looking like when I started them, and then we started a process for taking what we had and put it into a structure that can be supported on the cloud, so we can scale out. And this is basically what I'm going to show you today, what we did, how we did it, and some lessons that we've learned. My hope is that by looking at what we did and where we came from and where we are going right now, it will give you some ideas on how to attack problems that you currently perhaps are seeing, or perhaps allow you to design better software going forward. We basically, Bazila, what we do is a lot of software as a service. Okay, we have many services sitting on top of a search engine. We're basically on the search engine business. And so we are building and designing a lot of services on top of that. So what we are going to see is how we are designing our system to be more of a service-oriented. Okay. So a bit about myself. I started, just a quick show of hands, please. How many of you guys are .NET developers? Okay, how many Java? Linux? Okay. So I started my professional career as a .NET developer. I've been working on .NET for years now. I've been working on RavenDB. How many of you guys know RavenDB? Nice. And I've been working on RavenDB for about a year and a half as a core developer. I'm currently writing a book on that, and I have one book to give away. I need to figure out how I do that exactly. So I've been really into .NET. And about a year and a half ago, I started working for another company, which is a Linux-based. And suddenly the focus changed, and I started doing like everything in Java, everything on Linux. And it got me converted. I'll show you my workstation in a bit. So we do a lot of search technologies, and this is really the strong background that I have is on search technologies. This is Lucene. How many guys know Lucene? Great. It's Elasticsearch, which is some sort of wrapper around Lucene. Lets you really work very easily with Lucene. How many guys know Elasticsearch? Okay. So everyone who knows Lucene and doesn't know Elasticsearch, you really want to look into it. And basically, we are a Lucene shop. We've always been a Lucene shop. And we had to somehow redesign what we've been doing for the last couple of years. And this is the process that I've been doing. So this is my workstation today. That's the two screens. There is one Linux machine. This is my Windows laptop, and this is this MacBook. So I'm working simultaneously on 3 operating systems, not something that I will recommend, but honestly, my Windows machine in a couple of months will just go to the trash or something. So we are Bazila. Let you watch this for a second. So to be able to do that, we need to handle a lot of data, right? I said we are in the search engine business, and that's not entirely correct. We do collect a lot of data, but we're not only searching on that. We're doing a lot of extra processing. So we need to hold some sort of a search engine, right? And it needs to be somewhere, but we have to have services that can run on top of that, of the data and process it and do some a lot of smarts, and that smarts can take some time to run. So I will show you a bit what we do in Basil, how our screens looking, what we're trying to do, what we're trying to accomplish, and then I'll show you how the actual architecture that we had in place worked, how it looked like, what it meant for us. Then we'll try to see how we can take such an architecture and move it into an architecture that is able to scale out, because I think we multiplied the amount of data that we had in the time when I started in Basil, and today we multiplied the amount of data by 10 or something like that. So we scaled out quite massively, and we are still expanding. And then we are trying to look at some DevOps operation. DevOps is the new way of managing servers, of managing architectures, and I'll show you some stuff that you can do with that and the logic behind of that. So let me show you our system. Second. Yeah. So but the Basil system is basically just a website for a lot of our users. You have some sort of a search engine that you can search on. And if I'll be looking for London, I get results just like you would expect in any search engine. Healthcare is a big issue right now. And you see that we catalog the actual results by various types, and then you can sort on that, you can filter on that, but we can also show you the segmentation of the results. So if I'm doing this search here, okay, search resolution isn't that good, but you can see I can tell you that we had results from mostly social networks, and also some articles, blogs, and forums, and also Twitter. So we know how to break things apart. We can also see the actual trend, the actual chatter volume that is being the thing that I'm looking for, how much it's been discussed. You can build complex queries, and a very nice feature that we have, we can show you some insights on things that you haven't even thought of. So for example, okay, sorry, this one is going to take a couple of seconds, but this idea here is it's going to process the results and somehow extract some additional information about your actual query. So if I'm looking for healthcare, it will show me some things that are related to healthcare. Like if someone is talking about healthcare and is talking about healthcare in relation to some other topic, it will show up in this search. Okay, I have another example that I've already captured the screen of. The reason it takes so long is because it actually does a lot of processing in the background, and it's been done on a distributed environment. Now, currently it is distributed. It works a lot faster than we had before, but as you can see, we still have quite a lot to do. Okay, let me go back to the slides. So that's our system. And the way it worked before, when I actually started working for Basil, it looked like that, basically a whole mess of stuff. So we have servers, right? And each server is going to run different stuff. So we have, I don't know, this process and that process, and web UI using Play, and in our Lucene engine, which basically took a lot of data and processed it, and our crawlers, which were working and getting the data. And everything was like in one huge mess. And our way to manage that was using SSH terminals, consoles, a lot of like really black magic that was going on all the time. So there is this rule when you start an architecture that you need to scale up and then out. So we were scaling up quite rapidly, and we didn't have really where to go next. So we got to a point where we really had to scale out. So the problem was that we had this mess, and basically we were in chaos. So we really didn't know where to go, which track to choose, which we really had to somehow make an order. Now, this not only that we couldn't really grow anymore, we got to a point where if something broke, we didn't really know what broke. We need to somehow figure out things based on I don't know, like, grep on logs on like dozens of servers and with SSHs and really messy stuff. And we didn't even know when things broke. So something just didn't work, and we didn't know what exactly broke in the system, and we had to trace it down. And this thing could take whole days. So we ended up spending a lot of days just making sure the system is operating, and that really was the straw that broke the camel's back. So how did we actually get to that point where we had this mess? So I don't know, like, there is many types of companies, but in our company, we pushed very, very hard forward. We always had to push forward. I'm only there for a year and a half, something like that. But even long before that, this was the spirit of the company. This is how the company worked, and it's fine. It's how you get things done. You just push forward. If you have something breaking, then you just fix it with a patch, and it's fine. But over time, those patches, you make a patch on top of a patch, and at some point you just get to that mess. And whenever we had a failure, we were ending up spending days on just solving that. So, to my opinion, when half your business or something like that is on like actually fixing bugs or fixing the architecture, and it takes you a lot of time to figure out what goes on and how to fix what's wrong in the system, that's probably when you need to start thinking about re-architecturing. So why do we care about re-architecturing? I don't think it's only about being cool and Jedi and all of that kind of stuff. I would want to hear your opinions there. What do you think that a good architecture gives us? I have a book to give away, guys. Yeah.
The ability to maintain a large system, because if you don't have an architecture, it gets way too complex when the system gets bigger.
Yeah, sounds right. Something else?
More transparency about the problem stages.
Okay.
You can easily spot where the problem is.
Yeah, so architecture is modularity. That's basically what you're saying. Is not having like this huge ball of services and servers and everything. So the modularity, an architecture gives you a modularity, and that modularity gives you the ability to replace components, to add new components, to debug a component, to test it properly on your actual system or within your development environment. It also lets you to deploy things way faster. So in our original architecture, if we had something broken and we had to fix it, we would somehow get into the system and replace that component. But because everything was so tightly coupled, we didn't know what would be the effects. So we would replace one component or fix one component, and then some other component would break. If the crawlers were broken and we fixed the crawler, a parser or whatever, so we suddenly found out that one of the indexing operations just failed because it wasn't compatible with the new crawler version. that's really, really bad. So again, once you have modularity, you can actually debug things way better in your system. So you don't have to deploy and find out that something else broke, because everything is modular. You can test each module separately, and if you design things correctly, you can actually fire up a new testing system locally to your development environment. It's also much easier to monitor. You can actually find out if something broke, and if something broke, you know exactly what broke. And we are actually going to look at tools to track that. It's also, you come to a point where you are crash resistant. So if something breaks, it doesn't mean that your whole entire system breaks. So in our original application, and we will abstract this away in just a minute, if we had a search engine break, our entire system was down because the web interface was doing the actual searches on top of the Lucene indexes. Now, again, if you start building from scratch and you want, to time to market, you want to deliver something really quick, it's okay if you do that, but if you keep operating on that for years, you end up with such a system. And another problem that we had is that whenever we had new people coming into the company, it took them months or weeks or months to just understand how the system works and understand each component of the system and how each component can be, you would give them a simple bug to fix. It will take them days to understand what's going on. So we really, really needed a change. Not only because of those problems, but also because we really grew and we just started getting a lot of more data. And we had low availability because it took us days to fix stuff. We were ending up having our entire system down for, I don't know, like too many percentages, right? Too many hours a week. And we really needed to move away from that. So for us, the goal was SOA. I don't know, I just took a random image from the internet. I hope this makes sense. The architecture, the SOA architecture, service-oriented architecture, is basically what you would want to have in your system in order to achieve that level of modularity. That is, you take your system and define modules that you can build so each module can behave separately. So there is one interesting fact about SOA, though, that even if you break things apart, you don't want to break them too much because you can end up having the select n+1 problem when you have in SQL servers or any SQL database where you actually make too many calls to the database to get too much info. How many of you guys know what select n+1 is? All right, so in select n+1, you make one query and you get data, and then you continue asking the database for further data for each and every result that you get. So if you break things apart on SOA too much, you end up having this exact problem. So you get one piece of data from one service, and then you have to query that service or other services for more information. So you really want to have encapsulation working good, so one server can give you a full answer for your query. So what's interesting about SOA is that it's very easy to understand what services that you need if you think about layman's terms, right? So if you think about how my system would work if it was built 50 years ago, not using computers, and you start thinking in terms of how your system would behave like with human beings doing the actual work, then suddenly everything clears up. And we'll see an example for that in a second. So how do you approach re-architecturing? So the first advice I have for you is talk with actual humans, with actual people who understand the business. So there are a lot of agile talks in this conference. That's basically the spirit of things. You really want to understand what the system does. Don't try looking at the actual system that you have today assume it works correctly or it does what it's been expected to do, and then just redesign the code. You don't want to do that. You want to understand what the system does, think in layman's terms, and build the services one by one based on that. So in order to do that, you need to think abstractly. You need to think, again, what the system does and how I would have done that if I didn't have a computer. You need to prioritize. You need to understand your priorities. You need to understand what services you want to replace now and what services you want to leave in that whole mess that you have and somehow integrate it or somehow leave it for another time, maybe even bring it down for the time being. And then you want to establish some sort of a testing environment or at least a way you could test that whatever you do is good. So perhaps you would want to make some comparison to the old system, maybe have that automated. That's not entirely necessary for all scenarios. For example, I will show you in a few minutes, we had a scenario where a comparison wouldn't really make any sense because we switched to a component which is too deep in the system and it was just starting to behave differently, and we just accepted that difference and moved on. So a comparison doesn't always make sense. And whenever you change stuff, you really want to see that it works correctly. So before you actually deploy it and before you move forward, you want to make sure that the actual component is not buggy in itself, and that's quite obvious. So our old architecture, if we try to abstract away the way that our previous system worked, we basically had crawlers, right, going through the internet and fetching data. Now, that data would then be processed into an index, into a Lucene index. Basically, it would have been processed for search. And then that crawler would have done the entire job of actually going to fetch the data. And once it got enough data, it will index it into a small index. And then after some time, it will throw the index into some pool. And the actual servers, which are the data servers, will take the indexes, the small indexes, and every couple of hours merge them together to the large index, which would then be searched using all of our services, or at least our website. Now, that's quite broken, but this is, if you start to abstract things, this is what you have. You have, on one side, you have the actual crawlers doing the actual crawl and parsing of the documents from the web, and then preparing the small Lucene indexes. And then you have, on another side, the third step, what I call here, you'll see in a second why, we have the actual data servers, the actual big index that we search on. So if we abstract things even further, we have the crawlers going and fetching the data. As a second step, they actually make the index. And on the third step, we send the small indexes to the large index to be merged. That was the indexing part. This is the search part. So this is, again, the same data cluster, the same the data servers with the huge Lucene index. And this is our the play, which is the web framework that we used, accessing the actual data cluster to perform searches. Again, that's actual web interface, actual website doing actual searches on Lucene indexes. As I said, what this causes is that whenever we have a problem within the actual Lucene index, the web interface wouldn't work. Or even worse than that, by design, every couple of hours, the indexes would go to that pool and get merged into the actual large system. So a merge can take a lot of CPU and I/O power of the actual cluster. So the web interface itself would behave much slower because the actual servers, data servers, were really busy. So to understand how we can attack this problem, I'll just one slide. I'll quickly explain how search engines work. So whenever you have documents, for example, we just crawled those 6 documents here, a search engine will take each of those sentences, each of those documents, and process them into a table alphabetically sorted. So that's some sort You can think of it as a dictionary, but stored on disk, and it's alphabetically sorted. So whenever you add a new document, it will break the actual text apart into words, do some normalization, and throw each and every word into this table here. Now, whenever you add a new document, you have to update this table. And whenever you take a few of those tables and merge them together, you have, again, to read the entire table into memory or whatever, and then merge the tables. So it's quite a lot of work. So what we had in place originally was taking that table and pushing it to a pool, and then merging such tables every couple of hours into larger and larger tables. So that's the scheme of things of how we did it. But basically, if we wanted to have a distributed search engine, we would actually have three options. So one option is doing that, is having one large index and having many small indexes being thrown into a pool and merged together into this one large index. Another option is based on how Lucene actually works. Lucene doesn't necessarily imply that if you have one index, you have one set of files. Lucene actually writes incrementally. So I can take one index and move it along, and then have that same index still updated using segments. So each segment will create a new set of files that I can move away. I will still need to merge it to some extent, but it's much cheaper. So we could have went that road, but as we'll say, when you talk about distributed environments, you want to minimize the amount of network traffic that you have. That's called the fallacies of distributed computing. We'll see that in a second, but you can't assume anything about the system, basically. One of the things you can't assume is that you have a network and the network isn't busy, and et cetera, et cetera. So we wanted to minimize the amount of network traffic that we had. So the solution was basically to, instead of actually have the crawler index stuff and then throw the indexes into the pool, we just decided that we'll go with the abstraction all the way. We'll just tell the crawlers to crawl and do whatever they were intended to do, and send the documents that they crawled somewhere. That somewhere, that thing that they will send it to, will do the actual processing of the documents into an index and have it searchable within that large index. So this is where we got to Elasticsearch. Instead of reinventing the wheel, we already had in place a system that indexes a lot of documents into discrete small indexes, and we took those indexes and threw them into a large index. We already had that in place. We could improve on that and actually now use the segments approach, which would make things a bit faster. But again, we really wanted to minimize the cost. We really wanted to get to a point where we have just small documents moving around the place. And we also wanted to achieve high availability. We wanted to be able to say, okay, this is our index. It is being replicated among different servers. So if one server goes down, the index is still accessible. Elasticsearch has all of that implemented already and very highly tested. It's being used by GitHub, but I think Stack Overflow. Really large players already are using it, and it's really highly tested. And I actually know the guy who wrote it, and he knows his stuff, right? Chai Bannon, he really knows his stuff. So we decided to go with that. There is another saying here, because we really didn't want to start implementing such a huge thing all by our own, right? It's time. We really wanted to use something already tested. So using existing components, it's really SOA 101. So Elasticsearch is really nice, really easy to work with. You can just fire up a cluster by just running a few JVM instances of Elasticsearch, which is written in Java. You just run multiple instances of Elasticsearch. They negotiate with each other. They elect a master. Just everything works just out of the box. It has a REST API, so you can virtually access it from any client. If we talk about how to create a service in a SOA environment, Elasticsearch is really built that way. So now that we selected the technology, we needed to figure out how we can make a huge index operate. Now, you really don't want to go and just say we have one huge index, because that's still scaling up, right? You would have one server maybe replicated, but you still have the capacity of that server. So really, we needed a way to scale out. So while we replicate and we can shard, right? We can have one huge index, and that index could be sharded, and each shard will contain some specific data. So we could use the naive sharding implementation, which basically will use some hashing function on the ID, on some property, and throw things away. It will select a shard based on that function. We could do something like that. For us, the better option was to use a technique called rolling indexes, because we index stuff as they go, a lot of documents as they go in. If someone wrote a Facebook post, and we'll index it just the minute that we crawl it. So we basically are time-oriented, right? Whenever a document comes in, we care about when it came in, because we want to alert our clients, et cetera, et cetera. So we really were time-oriented, so it made a lot of sense to us to actually index into blocks of time. So you could have weekly indexes, you could have daily indexes, maybe monthly indexes, depends on the amount of data that you have. But for example, we chose to use weekly indexes, and then we had the notion of archiving. That's something that already existed in our system, and it took us a while to realize that. But our business operates on top of that we always provide access to up to a year or 2 years in the past to data. So we already had the notion of archiving, but really had to have, weeks of discussions until we realized that. Once we realized that, we were able to actually design the system to have weekly indexes. So what happens today is that whenever data comes in, it is indexed into that index that represents the point of time or the block of time that we are in. And that way, we can actually move forward quite efficiently. If we add new servers, the indexes of those of the new weeks will just go to the new servers. And once we progress over time, we'll just add new indexes. Right? The week 7 is the new index. And as time progresses, we can just remove old indexes. Because again, we already have the notion of archiving in our business. Now, this actually solved us quite a lot of problems that we didn't even think about. Because the way we were working before, we had a lot of duplicates. The way that the crawlers were just merging stuff and merging various indexes, we were ending up with having like a big index in multiple servers. And because of some design decisions that they made with the old system, we had duplicates. So whenever the users search for something, the web UI would have filtered out duplicates. And it's quite common to find duplicates in distributed system. But using this approach, we would know exactly where to put each and every discussion, except, for example, if the crawler decides that the discussion date was moved. So that's rolling indexes. So once we moved to Elasticsearch, we basically did that because of the fallacies of distributed computing. That is, all of those assumptions, we'll go through them in a second, that really didn't solve all of our problems. We still found out that even Elasticsearch still has a lot of problems with networks. And this is why I put this here. Who knows about the fallacies? Have you heard about them before? Right, so this is basically whenever you try and start approaching designing a distributed system, you really have to assume all of those, and there are some people adding even more right from the get-go. So first, the network is reliable. You cannot assume that. The network is not reliable. Computers are not reliable. Computers will crash. The network will not be available to you. latency is 0. You cannot expect to have 0 latency latency on your operations. You have to expect that some things will take some time, and everything will take at least some time, but not everything will be noticeable enough. Bandwidth is infinite. This is, for example, the reason why we moved to transferring documents around instead of indexes. We didn't want to abuse the bandwidth. The network is secure. We don't really have to assume that in our scenario, but it is something you really, really have to assume. I know I contradict myself, but for us, we're using private cloud, so it's less of a concern for us, but it is still something you really need to assume. So you would integrate authentication within your services. Topology doesn't change. There is only one admin. Transport cost is 0. The network is homogeneous. All of those you cannot really assume in any system. So luckily for us, we are based heavily on Elasticsearch. So Elasticsearch already assumes a lot of that for us for the indexing part, but we still had to build services on top of that architecture, and we really had to assume all of those things. So this is how the new system looks like. We have crawlers, and the crawlers produce JSONs or XMLs of data, and we have our Elasticsearch cluster. Now, we needed somehow to transfer, right, those documents from the crawlers to the Elasticsearch system. So that's Elasticsearch cluster talks, it handles the messaging between servers all by itself, all right? So if you bring a cluster up, the servers know about each other within the cluster. They will negotiate stuff. You execute a search against the cluster. The servers will negotiate between themselves who will execute the search, return results. The Elasticsearch cluster is mostly self-contained. But whenever you need to talk to it, and for example, we have quite a high stream of data coming from the crawlers to the actual Elasticsearch cluster to be indexed, we needed some way of delivering it. So, and that's where the messaging systems come into play. So messaging systems are what actually orchestrate any good service-oriented architecture. You can either have a broker-based messaging system, which is RabbitMQ, ZeroMQ, Redis, or you can have some sort of a service bus that negotiates everything, and there is no central node that can go down. So a few notes about messaging, stuff that we learned a little bit of that in the hard way. So you have two basic types of messaging. One is synchronous and one is asynchronous. So the difference is mainly about blocking, right? So if I send a synchronous message, this message that I send, I will not be able to resume work until I get an acknowledgement that the actual system, the actual receiver got the message and processed it. Same goes to the receiver. The receiver will accept the message and it will not continue work until he finished processing the message and possibly even sent a response. An asynchronous messaging process will not assume that. You just throw the message away. I mean, not throw it away, but just notify someone about something and move on. You don't really care about whether he processed that or not. Another type of messages, another style of messaging is whether the message is durable or not. So a durable message is basically a message that it is being stored somewhere. So if the broker goes down, goes back up, and it can just recover and continue from where he left off. A non-durable message is basically like me saying something to someone to do something. So it's not documented anywhere. And if the broker of the messages is going down, when he comes back up, there is no remainder nobody will remember that there was such a message. Another type or another property of messaging is whether it's a one-way messaging, a request reply, or a pub sub. So again, it's whether I'm telling someone to do something or I'm asking him a question and waiting for an answer, or I'm waiting for notifications for something, or I'm notifying a lot of other people. So one-way messaging is me telling someone to do something and just going away. And that's orthogonal, basically. So I can tell someone by heart and move away, and that's a non-durable message, right? I can tell someone and wait for his reply and not move along until I got the reply. And also, I can do that either by heart, or I can just wait for his, or we can just write it down for him on a note, and then it's a durable message. And PubSub is basically me subscribing to someone's notifications, or someone is subscribing to my notifications, and then I can have multiple subscribers doing that. And commands and events are basically ways for me to, it's ways to define those types of communications. So for us, we really needed durable messaging, right? We didn't want to be in a situation where the broker goes down and we lost a lot of messages. So that's durable or not durable. We don't really need to wait for acknowledgements. We want to wait for the actual delivery acknowledgement, so we would know that if we put a message, it was really put, it was written to disk, or it persisted in some way. So that's one thing, but we really didn't have to wait. For example, if I send a discussion, a thread that I read from the internet in the crawler and put it in, to the broker, I really don't have to wait until the indexing process takes it, because there may be a spike right now, and I don't want the crawler to wait. So we are using a synchronous messaging, but durable one. And again, the crawlers are a one-way messaging. They basically take the message, they take the actual thread, and pass it along to the indexing process. Now, they don't really pass it along to the indexing process. They just put it in the broker in a specific queue, under a specific queue name, or as I like to call it, a channel. So we have a broker, we have multiple channels, and each role of the system knows about the channels that it needs to know about. So the way it works, a crawler crawls the data, and it puts it under, gives it to the postman, and tells it, please put it under this channel or in this box. The indexing process knows how to get to the postman and takes all the data that for indexing from that specific queue, and that's how it works. So there is one thing I want to add. I will do that in a second, but there are a lot of things that we still have to consider when we deal with messaging. It's not just I have a message to give someone and I will just put it in the queue and I'm done with it. I really need to make sure that whenever I'm writing a message, if someone else writes the same message, that nothing will happen, either in write concurrency or whenever the actual message is being delivered, and if it will get, for some reason, it will get delivered more than once, then nothing bad will happen. So in our system, we index the actual documents that we get under an ID, which is the URL. So if we get the same message twice, nothing bad will happen, because the message will just override the new document, the new discussion. Now, we could lose some data. For example, if we had two crawlers crawling the same data and putting the same message, and one crawler crawled the website a millisecond after a new reply was added. So we might lose that reply, but in our business scenario, we don't really care, right? So if we lose one reply out of one discussion in, I don't know, in even 1,000 discussions, which is quite a lot, it is not something that is business critical for us. So we had to really make that decision based on the actual business needs. And if the business tells us that we handle so many discussions, if something like that would happen, it's not that big of a deal, so we are good with that. So there are many queue implementations. There is MSMQ, RabbitMQ, ZeroMQ, really a lot of implementations, and you would need to find something that works for you. For us, it was RabbitMQ basically because it is stable enough. I think it only crashed once in a couple of months, and that's also because we didn't have enough memory for that. But basically, it is very stable, and we just picked it, and we are very happy with it. There are many other considerations, obviously, but that's really a matter for research. Now, there is, between different messaging technologies, there is something that's called the delivery guarantees. So you would have to choose a messaging system that has the delivery guarantees that you require. So for us, we really wanted to have at least one delivery guarantee, and RabbitMQ delivers that. So this is something that you really have to take into account. Redis, for example, doesn't have that. Redis doesn't necessarily deliver each and every message that you give it. Let me go back. I have that in the continuation, but I want to put it right now. This is the system that we have. So we have crawlers, and the crawlers send discussions through the postman for indexing. Now, we have another part of the system which is called alerts. So we want to be able to notify our clients whenever a new discussion that is related to them comes into the system. Now, one thing that we could have done is take that same message that is being sent for indexing. We could take that message and do the alert check on that message using the same process. Another thing that we could have done is take the actual message, index it first, and then have one server pinging the actual cluster every couple of, I don't know, seconds, minutes, depends on the actual business needs. We didn't go with either options. So we didn't want to heavily ping the cluster, throw many queries on top of the cluster using some sort of alerting system, because we have a lot of alerting queries, and we didn't want to have so much stress on the actual data server that it's being used for actual searches and a lot of data processing. We didn't want that. And we also didn't want the actual indexing process to perform the alerting. We actually tried that, but we discovered that it's so heavy, and we didn't really want that because it would affect the way that we acknowledge messaging. That if we send a message from the crawlers to indexing, that then the process that just got the message, it will notify the postman to release the message, because I handle that, you can delete that message. Now, and it should take, I don't know, a couple of seconds most, but if you end up having this process take too much time, then it might time out, you might have errors during that process, and you might not acknowledge, you might end up doing too much work over time. So what we did, we created another channel. You can do that in various different ways, but each crawler is now putting the same discussion twice in two queues. One queue will go for indexing using one service that is sitting somewhere here, taking messages from the postman and indexing them. And another channel will have the same discussion, but we will have another cluster sitting somewhere here, another cluster of servers taken from that channel only for the alert system. So that's SOA. We just got the benefit right out of the box the minute after we implemented the actual indexing cluster.
Can I have a question?
Yeah.
It looks to me that this additional channel needs also to perform indexing before we can issue an alert.
Why so?
Because how else you can identify which message to is alerting about?
I'm not sure I'm following. If we had two posts on Facebook, right? So this crawler took two posts from Facebook. Two of them went through one channel and got indexed into the cluster. The same two are also been put on the other channel, and this cluster here will take them one by one. So the cluster took one message. We call that percolation because that's how the feature is called in Elasticsearch. but basically it percolated on that discussion, the first discussion, and for example, it didn't find any match, it will act the message, it will acknowledge the message, and the message will get deleted. We'll then have the other message from that second queue being percolated, and we found a match, and it will acknowledge the message and do its thing about sending the alert out. So that cluster here will do the percolation. Percolation basically is a very efficient way of indexing into memory and then executing thousands of queries.
So the second one you're doing sort of pub/sub type content based.
It could be it's not a pub/sub exactly, because I only need one of the servers in the percolation cluster to do that.
So I meant the people who wanted to be alerted about it.
No, because we send out alerts, actual emails, not within our system. That's the concept of one way, basically. It's not a reply.
If you send these two messages to two different channels, do you have any guarantee about the order in which the cluster will?
No, and that's the point that I have here. So I mentioned that earlier. The question was about the actual order, and I mentioned that earlier, that if two crawlers have indexed the same discussion, but in a gap of a couple of milliseconds even, and one reply was added, then I can potentially delete one of the new replies. But again, that's a business decision that I don't really care about. The same thing goes with alerts, because I can send out an alert. You know, I have a discussion with 10 replies, and the 10th reply is what triggered the actual alert, and I will send it out, and then I will get the same discussion again. So I don't want to send another alert. So that's what we call idempotence, or I don't know how you guys pronounce it, but the idea is that if I get the same message twice for processing, or if I get one message and then I get the message that I had to get before it, but I just got it after, then I will not do any stupid stuff, right? I will just behave normally. I will know to tolerate those kind of stuff. So I really have to take into account whenever I do that, again, the delivery guarantees and the actual scenarios where we have race conditions and errors. And if, for example, what happens if I have an error with one message? I can't parse it, for example. I don't want to throw it back into the postman's queue, because it will just go back again and again, and I will have this problem again and again. So in the process that actually reads the messages, I want to be able to detect this. If I have an error, I will just retry on the same server, and if after a retry and trying to fix it automatically, I cannot do anything with it, I will throw it away somewhere that I can process it later, even manually. So that's also one thing that you want to consider. So on we went, and we architectured the system from scratch and implemented the Elasticsearch cluster, the messaging service, the percolation service, and then along the way we took a decision. We had our reasons, but we did it, and we swapped a very fundamental piece of software within the cluster. Specifically, it was a stemming algorithm within the search engine. So if in the old system you would be searching for something and you would get no results, in the new search system you will get results, because we became smarter. Specifically, it was a Hebrew stemming algorithm. I think it was a good decision that we made it, but it introduced so much more complexity. So that my suggestion to you is not to do that. Just re-architect, make sure everything works as it worked before, but not do any further changes. Give it a while to stabilize, and then introduce those new features. For us, the actual experience was that we replaced that component, and because the entire system basically changed, and suddenly, for example, the duplication concept was gone away, and a lot of concepts changed, so it was a good opportunity for us to also introduce more changes. So it was all right, and we survived that, but it prevented us from releasing on time, and we were late in a couple of months, and that's something that you really should notice if you do any sort of such thing. Also, when we launched, we had a huge fail. We launched, we ran for a day, we had a huge problem with the alerting system. Again, that problem eventually turned out to be a problem with the new stemming algorithm that we used for Hebrew. So again, that same problem that prevented us from going up earlier also made us turn off the entire cluster, revert back to the old system, and continue for a week or two using the old system, and then going up, launching again. So my advice to you, don't introduce any new core changes. You're doing, when you're doing such an operation, such an architecture operation, that's basically a surgery. You replace the heart of the system. So don't introduce any new concepts. So query migration is a whole new process that we had to do when we got to that place that we really had to somehow migrate old queries to the new queries because of the new stemming algorithm and the alert system we already discussed. So just a small note, when people talk about the cloud, they talk, I think the term is a bit vague. There are many types of clouds. For us, when we talk about a cloud, that's basically a couple of dozen servers that we have running in the data center somewhere. It's our metal. It's running. It's actual machines that we own, and we run them. But it's also the ability to run the actual services that we have on top of EC2 machines, right? Spawning a new machine from Amazon clouds and stuff like that. So when you architect for using SOA, that's basically you get that for free because you're so modular that you can run anywhere, and you just have to make sure that your services do not use anything that can prevent you from running on EC2. So that's the bubble thing. Let's see if I got results from the other. Yeah. So I don't know what's going on in London right now, but so that's the bubble that we got. We call it a bubble because we searched for healthcare, right? And we got those results. We got health reform, Affordable Care Act, Healthcare SY. I'm not really sure about Obamacare. I'm not really sure what all of those mean, but basically I performed a search, and some algorithm went on top of those search results and was able to give me various terms that have been used in conjunction with my actual query. So I have another result here. Second. So I have another result, which is I queried for London, and I got all of those. So Hyde Park, I get it. Wembley, I get it. I'm not quite sure there is something going on with Roger Goodell. I Googled for it. I'm not quite sure. There is, I don't know, AFP and Fashion Week, probably things that are going on right now. Now, this really depends on the amount of data that we scan, and we might not scan a lot of data from London specifically. But this is an algorithm that we have in place. Basically, you issue a search query, and instead of getting actual results, you get this graphic here. And that graphic, there's actually more terms. It just displays the top 10, and then you have a table showing more. But it does a lot of text processing on the actual results that you get. Now, if you do that sequentially, right? If you perform a search, get all the results back, and then go one by one, this will take a lot of time. So what we did was use the actual Elasticsearch cluster that we have and introduced a plugin, an Elasticsearch plugin that will accept a search query, and instead of returning search results, it will, on that specific shard that it runs in, it will take the results that it got, perform the actual operation, and return a partial result. Okay? And the master that actually got the actual request will gather all of those shard responses, integrate them into one large response, and this is what we get back from the plugin that actually got the request. So the way we did it, the original way we did it was sequentially. We just performed the search, got the results, performed the actual algorithm, one document by one, and got back this nice thing here. What we did now, because we wanted to be able to scale out and make this even faster, and the more documents that you give this algorithm, the better results you get, and we did want to have more documents to be processed, we really had to scale it out somehow. So instead of inventing our own mechanism to do that, we basically created a plugin within Elasticsearch, which gives us a really nice way of doing that, and we just got scaling out for free, because Elasticsearch will manage everything for us, the whole shard negotiation. We just perform the search and integrate within that search request to using the results that each shard got to perform this bubbling operation. So leveraging some ecosystem or some infrastructure that you already have is something really, really useful, and you should really look into it whenever you got a chance. Now, assume something goes wrong here. We had a couple of times that we got results that didn't really make sense. For example, you see here we have the chatter volume, and the color of the bubble represents if it's new or something that's been discussed over time. So we had many results that actually return everything blue, for example. A lot of results that really didn't make much sense. So how do you debug that, right? If you have a distributed system and you build a distributed system, and basically we built a distributed system, how do you actually debug or trace what's going on if it goes on, I don't know, like 10 servers? Even if it goes on only 2 or 3 servers, you still don't know out of your couple of dozen servers that you got, which server processed which part of the message and how to move along. So keep that question in mind. I will show you some really nice trick in a bit. Let me just talk a bit about scaling SQL. Our data storage was SQL Server, MySQL. It still is MySQL, but scaling it out is a bit of a problem a lot of times. We ended up basically moving to MariaDB, which is some implementation of MySQL. I'm not really sure about the politics there, but it got sold, and I'm not quite sure. But MariaDB is a MySQL that is able to scale out, and any SQL database can really scale out to some level, right? You lose the ability to perform joins between servers and stuff like that, but still you can scale it out quite nicely. But SQL Server isn't built for quite about everything. We do a lot of time make the assumption that SQL Server or MySQL is a silver bullet, and we just try to do anything with it. What's growing really, really strong nowadays is using what's called polyglot persistence, using databases that are not SQL. So except from those who said they know RavenDB, who here uses anything other than SQL database? Oh, quite nice. So I can just go through this quickly. Who's not? Who's never heard of polyglot persistence? You got in the book. Come after this session and I'll give you a free copy of my book. I found a way to do that. So basically, this table here is very confusing, maybe, but it really explains everything that's going on in that area. So you have the relational, non-relational, and then within the non-relational, you have multiple types of databases. So you have document databases, you have key value stores, and document database is basically a key value store, but with some added properties. You have graph databases, and then you have what's called the big table, which is the concept that really started the whole movement, if you wish. And then, I don't know, in the relational databases, I'm not quite sure what NewSQL is. It's some sort of, I don't know. I think people just got too confused about things. So this part here is representing all the databases that are not relational. That is, are not built using tables and rows and joins and SQL, the SQL querying language. And that's really, really how things are moving forward from now. So instead of just saying, I'm building a new application, I need a database, I will just use a SQL database, a lot of people today start building stuff on top of databases, of things that actually can persist data, but they persist data in a different way. The biggest benefit of all is the schemaless feature, right? So you don't have to define a schema in most databases. You just can provide it with some raw data, and depending on the actual use of the database, it will know what to do with it. So key value stores will just let you retrieve back data based on the key that you stored the data under. Document database will let you perform some operations using the document properties that you put into. Graph will let you realize, will let you connect different data things using some relations in the terminology of graphs, etc., etc. So this is something that we really did. We took parts of the system. We didn't just go and rewrite everything, but whenever we introduced new parts to the system, instead of just saying, okay, we have MySQL, we just shove everything within it, we just went and looked into opportunities to using different data stores that will fit our needs better. So it's polyglot persistent, but it's also use the right tool for the job and use the right database for the job, and it's really something that I highly recommend. But even if you do that, you get into arguments like this database is crap and this database is not worth using. So there is a really high critic on MongoDB, which is a document database, very popular one, that it's losing data. So whenever you are going to choose a database, just make sure you understand the consequences. So yes, MongoDB can lose data. It uses a lot of in-memory storage, and it doesn't persist to disk very frequently. So just make sure you know what you're going into. Another important thing about those databases is that they are not all of them are immediately consistent. So SQL database is immediately consistent. So whenever you do a write, part of your write will update the indexes, and when the next time someone will, you or someone else will perform a query, you are assured you will get the results that are up to date and include the last write that you did. Most of the other databases that I just talked about are not like that, are eventual consistent. So you will make a write to one copy of the database, let's say it's replicated, you will make a write to one copy of the database, and until that write, that thing replicates to the other nodes, other users may get stale results. Or it can even happen within one server. For example, in RavenDB, you make a write to the document store, but the indexes may take a while to update. So again, you may have other users getting stale results. So it's really something that you really need to take into account. And I don't think it's a bad thing, eventual consistency. It's mostly how we are used to living, actually. If you make an order in Amazon or eBay, it's not guaranteed to be there for you. You might get a refusal even after you pay. If the sun exploded 8 minutes ago, we'll only know about this now because it takes that 8 minutes for the light to come until we'll see that. So eventual consistency is how we are living, basically. And if, we just got used to immediate consistency on SQL-based servers, but it's not really how we should build our system with. So that's another thing that I really think you should take into account. And when thinking about it, you don't really have to use the same database, or not only you have to use the same the right database for the job, you really have to use the right tool for the job. So use whatever language makes sense, use whatever platform makes sense. Don't be afraid of even mixing platforms. There is one very big company here in London which actually has both Windows and Linux servers talking with each other on their system, very huge system. So it is possible, especially if you build SOA applications. Let me wrap up with talking a bit about logs. This is one very critical thing for us. So if something goes wrong, the way for you to know that something really goes wrong is by looking at the logs, right? But how many of us really know how to work with logs? And if you have dozens of servers, how can you actually aggregate all the data from all the logs? So there are many such tools, but even if you actually get the logs, there is a really nice XKCD about someone, a superhero who actually knows regex and Perl and Python that goes into the, comes whenever they need him and does this regex thing and is able to figure out what just happened. Not everybody is like that. And we don't want to rely on those people who are. So we really need some sort of a tool and to do this for us. And that's basically what we found. There's a tool called Logstash. Anyone here heard about Logstash? Cool. So Logstash basically knows to take logs, to parse them, to dice them, and then send them to some sort of a storage engine. Now we are Elasticsearch shop, and I think that it's the recommended storage engine for Logstash. It's Elasticsearch. So basically, it knows to take a log. A log is basically a line with a timestamp and some data, and it will take that line. It will parse it using some parsing rules that you provided, and it will store some sort of a JSON document that it produces based on your configuration into Elasticsearch. What this gives you is using tools like Kibana, which I'll show you in a second, to actually walk through logs and be able to understand what just happened. You can graph things. You can the Logstash filters can even tell you based on the IP address of someone who actually made this and graph the actual world map, colored world map to show you things. Let me show you. So there's a really nice Kibana demo.
Is Logstash easy to set up? Because I tried
Yeah.
with Splunk, which is something like it.
Okay.
That was really hard.
So I don't remember his name, but I think Russell, the Logstash author, says that if Logstash is not easy to set up, it considers that as a bug. So my answer to you would be yes. We didn't have issues with that. There is even I don't remember the address. There is Logstash uses something that's called grok in the configuration instead of actually writing regex. A lot of times you can just get away by writing the named regex. So they already have patterns ready for you, and you just have to say, I want this pattern here and then this pattern there, and it will just work. So it even has a web UI where you can put your line of log and just experiment with the regex and the named regex patterns that he has. It's called grok, the actual way of parsing logs in Elasticsearch. So for example, this thing here is using this is a line from Apache, probably, some web server, right? So you probably know that. You have the IP address, some date, the actual request, HTTP request, the client, right, and everything. I don't know. I think, yeah, there is more to it here. So you have the actual message, and a lot of those messages are being stored in files on some web server. So what Logstash can do for you is using the patterns that you tell it in the configurations, it knows how to parse out this line into multiple fields, right? So the agent will be this part of the message. You have the client API in another. A filter of Logstash can take this IP address and output coordinates on the globe. Also tell you what country it is from. It knows how to parse the extension, and so on and so forth, the actual response. So you can take a line of text and parse it out into like a really structured format. that format, then Elasticsearch will, Logstash will take that parsed content, that JSON, and it will throw it into Elasticsearch. Now, this is where Kibana comes in. Kibana will go and query Elasticsearch using Elasticsearch features to display the data in a very nice way. So what happens here is that there is a query, basically, that queries for all of those logs, but it wants to color the different types of files that has been served. And then you can see the actual graph here. You can see the amount of requests, and each amount is going to split up by the actual types that have been served. You can have pie charts, you can have everything. There might be, yeah, so you have many others. What you can do, basically, with Kibana, you can just build a dashboard querying Elasticsearch on a specific type of I don't know, of logs and I don't know, like faceting on that, and you can just save the dashboard and load it after that. So for example, I don't know, I've never seen that. So there is American gun deaths. You have a map being plotted. You have the actual, and some graph, pie charts. So you basically, it's a web UI that you can just add panels through the actual web UI. It's done through here. You add rows, and within rows you add panels, and each panel can have its own, widgets and so on and so forth. So that's really, really worth looking into. Now, if you remember, I asked you about debugging an actual distributed system. That's something that can really be useful to do this with. So you can take your logs and you can just output traces, and you can tell Elasticsearch to take those traces and plot them into some graph. Or Logstash is very smart in actually realizing that some part of the log is an exception, even if it's multi-line, and take that exception and show you that as well in a graph. One of Elasticsearch features is percolation. So you can actually you can have something running in the background and query the Elasticsearch you use with the Logstash to actually send emails whenever an exception is detected in one of the logs. Or you can just query Elasticsearch and alert you if there are too many requests, so you can manually add more servers. The possibilities are really, really endless. So that's something I really recommend using. So a couple of minutes left. I want to leave some room for questions. So do test, test quite a lot. There are many types of tests, right? So make sure you unit test your code, and then you do some sort of integration tests. You have end-to-end tests. I cannot recommend this enough. This is a good solution that we had. We had some bugs that, some bugs are really, really tough to find, and especially if your code is written in Python. So our crawlers are basically written in Python, and every now and then you just got stuck, or their rate is like, they start working really slow. So what we do is basically restart, and it works. And if it works, why not use it? So monitoring, we're still trying different approaches to that. So I said you can use Elasticsearch, the Logstash Elasticsearch, to actually monitor using logs parsing and even send out alerts when you need it. We tried doing something a bit else now. We try to write some sort of a sentinel a service that will run somewhere and will ping different services and send out. But monitoring is really, really important. You want to put some resources and efforts into making your monitoring running well. So what we found, we have a large screen in the middle of the office, and we just took one Kibana dashboard and we displayed there constantly, so we can see like live feedback on what's going on. So if our percolation service, the alerting service, doesn't perform well, we see that immediately. if the cluster status is not what we expect it to be, we see there. So immediate feedback alerts, whenever you manage a lot of servers, you really don't want to be ignorant of that. We saw that. I think a couple of last words, basically. The spirit of our company is really, it's really convenient. We're not an enterprise or anything. I don't have to fight a lot of bureaucracy, but we still are trying to move very, really fast forward. So at least I find myself really trying to balance between the ability to code things properly, right? Write code, the way code should be written and testable and everything, and the actual need to market actual products. So I haven't yet found a really good way to balance the two things, but it's a constant challenge to actually do that. So I always give Git as a good example. So anyone here uses Git? Okay, those of you who don't, use Git. Git is basically a source control management, much better than Subversion and CVS. It might be an argument, but in my opinion, it's much better. It was written by Linus Torvalds, the guy who wrote Linux, in 2 weeks using shell scripts. And today, it's one of the, I don't know, it's a really highly used product. And obviously, it's not shell scripts nowadays. It's much more contained software. But my point is that you don't have to write good software with the right tools. You can just write something and get something out running using the right tools and whatever, but not even requiring clean code and just throw it out and just refactor later as you get to the point. So it did happen to us, right? Bazilla worked for a couple of years using software that wasn't able to scale, but we got customers, we grew, and we expanded. Now we found the time to actually re-architecture. So you might want to keep the cycles a bit smaller, but that's definitely something I would advise. And be open source. Either use a lot of open source tools that are really great, or even try to open source some of your stuff. You'll see that if it's something good and it catches, at least to some extent, you don't need it to be like the new, I don't know. But if other people will use it, you will see that your skills are improving. You will see that your tools are becoming better and better. And I cannot recommend this enough. Know your tools, even if it's your IDE. If you use Visual Studio, I don't know, spend the, $100, $200 and buy ReSharper. It will improve your productivity in really great scales. If you're using Java, I can recommend IntelliJ. And if you use Git, how many of you guys know about Git bisect? Okay, there's not much to know, but the idea is basically to, if you know you have a good commit where your a point in time where you know your code worked, and a point in time where you know that you broke something, you can use Git bisect to do binary search on the commits in between, and it will switch the actual commits, and you will compile and test until you find the culprit, the actual commit that broke it. So yeah, there are a lot of things to know about the actual tools that you use daily, even if you don't realize that. So try to stay open and find out new things. For deployment, I'll do this really quick, but for deployment, we use Jenkins. You just push code into the repository, in our case, Git, and it will just automate the builds for you. You'll have to provide some build scripts, but the idea is it will automate the builds for you. And once something built, you can specify the rules, what to do after a successful build, and then you can do deployment. When you do deployment, you can use the blue-green deployment pattern, which basically you will deploy to one folder on a server or fire up a new cluster of servers and deploy it to them. and if everything goes well, so you just stay with the new version. If not, you still can revert back to the old version, which still is existing. That's something we did when we launched, and we failed miserably, and we do that with every release. You have that's basically the idea of a canary deployment, where you just throw a new build and let some people use it and see if you get feedbacks or if you get errors, and so on and so forth. So DevOps is the new, I only have a couple of minutes, but DevOps is a new way for actually managing an infrastructure. When you grow big enough, and it can even be like even 5 or 10 servers, you'll find this very, very useful. Instead of having Snowflake servers, that is, you actually have to configure the server yourself, and you have to repeat a cookbook or something for your servers, and you miss a step here, and you do things differently there, and you end up having many Snowflake servers. With Snowflake server meaning the server has its own configuration, very unique configuration, and reproducing that configuration is very, very hard. Instead of doing that, you want to get to a point where we have Phoenix servers. That is, you somehow can automate the way of building and configuring servers. So whenever you need to spawn a new server, you just run some piece of code, and that piece of code knows how to configure a server from scratch, basically from an operating system image. So for that, there are a couple of tools. There is Vagrant, which lets you do that locally and spawn new clusters. You can use Foreman, Puppet, or Chef to actually automate building servers from scratch. Not only you can spawn new servers, you can actually make sure their configuration stays up to date. Now, instead of updating a server, you can now just bring it down and bring a new one up with the updated configurations. It may get a bit costly, but it definitely may worth the price. Today we're still, we are still in the middle of actually making the transition to be fully cloud ready. All of the important stuff we already moved away from the old architecture. We still are introducing new projects. I wanted to show you some demo of rapid development. We won't have time for that. But the idea is that this process is always continuing. You always have more to do, more to learn. But once you start doing things right, you want to keep at that pace. You want that whenever a new project comes in, you already use the concepts that you know, that you learned, and not like extend on a legacy project. And that's about it. If you guys have any questions, I'll be more than happy to answer. Yep.
Have you tackled the problem of distributing large operations like transactional operations? Or do you keep transactional operations within?
So what do you mean by, okay, the question is about keeping track of distributed transaction, but what transaction? What type of transaction?
Well, say you've got one service.
Database?
Probably more business operation. The canonical example I've been using recently is raising an invoice where you also have to create serial numbers. So you've got a licensing server on one side,
Yeah.
you've got an invoicing server over here. And the invoicing server has to go, I want to create an invoice, I need a bunch of serial numbers, go give me some serial numbers.
Yeah.
So the transaction has to, you have to have two services which both live for the entire.
Yeah, so I personally didn't try that in distributed environment, but I know the advice is not to try and do that. I mean, distributed environments are broken by nature. You know about that. So basically there are a couple of ways to tackle that. Worst case you can do is just just fake things. So one way, for example, in databases, when you want to give ideas and unique ideas, you'd use algorithms like high-low, and you know about those. You basically you dedicate a range of ideas which are preserved serials, and then you give it to one client, and it just has it locally. So you can do that, or you can spawn a service that will do this in the background while you're still processing payment, and by the time that you process the payment, it can return the message back to you saying, here is the serial. If the payment didn't go through, then you just throw the serial away. But you can do a lot of things. The idea is, don't, in my opinion, don't try doing a distributed transaction. It doesn't really worth it. Any other questions? Yeah, okay, thank you guys.